Welcome to the lecture on titration. Titration is done using very controlled amounts of chemicals, and sometimes you can use dropper bottles, but we usually use a burette, which is a very tall, long tube with a controllable stopcock at the bottom that allows liquid to go in a very controlled manner, and then you can test the liquid at the bottom to find out at what point the pH changes. You usually use an indicator for a titration, so we're going to talk about all of these different things as well as the calculations that go along with titrations here in this lecture. So a neutralization reaction, what do you think about when you think about the word neutral? Well, hopefully you've experienced the pH scale and you're familiar with the fact that water is neutral and a neutral substance is at 7 pH. And so when we have a base mixed with an acid, it can react 1-to-1 to create salt and water, which is neutral. So a neutralization is really just this acid-base reaction that produces a salt and water. Now remember, salt is a general term that we use for any metal-nonmetal combination, all these ionic compounds. So even though table salt, NaCl, is the salt you're most comfortable with, if you saw MgCl2 or NaI or LiF, these are all different salts, and so you can get any combination of chemicals in that salt position. All right, so take a look at this, and what I want you to do is write the balance equation for the reaction that you see here. We have aqueous potassium hydroxide and sulfuric acid. What's the acid, the base, the salt, and water? Go ahead and pause for a second and see if you can do this on your own. All right, so maybe you need a little hint as to how to put this together. So I'm going to give you a hint and remind you that potassium is a +1, hydroxide is a -1. Sulfuric acid is made of hydrogen, which is a +1, and sulfate, which is a -2. And then they're going to take place in a double replacement reaction. So potassium will now be with sulfate, and hydrogen will now be with hydroxide. So using these charges, go ahead and try to come up with the formula for each of these substances. All right, now that you got that, hopefully you paused it while you were working that through. Let's see what the answer is. All right, so we have our balanced reaction, of course. 2 potassium hydroxides plus sulfuric acid makes potassium sulfate and 2 waters. Which one is the acid, which is the base, which is the salt, and which is the water? Go ahead and pause while you identify them. All right, so since KOH has the OH, that hydroxide would indicate that that's a base, which makes this the acid. Obviously, water is water, and K2SO4 would then be the salt. All right, so it's your turn. Go ahead and write out the balance equations for each one of these, and go ahead and pause this while you work. All right, hopefully you got the first one. Let's go ahead and show you that. All right, pause while you work on the second. Here's the answer to the second. Let's take a look at that. Pause while you work on the third. And here's the third one. All right, so hopefully at this point you're starting to get the feel for these neutralization reactions. So when we do a titration, what we're going to see is we're going to have one item whose concentration is known and one that's concentration is unknown. And by reacting them, we can find our unknown in comparison to the known using our good friend stoichiometry in our balanced reaction. Okay, so a standardized solution is a solution whose concentration is known. And this solution is slowly added to the unknown substance. An indicator tells us when the chemical has turned to a specific color. So we have all of these are different indicators that change at different pH levels. Erythrocin B will change right around the pH of 3. M-cressyl purple will change at a pH of 2. Methyl orange at a pH of 4. Bromocressyl green, bromocressyl purple, bromothymol blue, we use that quite often actually, it's a more common one. And then finally phenolphthalein changes Actually, when it becomes quite basic, maybe between the 8 and the 9, it will turn pink. All right, so when do we have an endpoint with a indicator? Well, if we're working with phenolphthalein, the endpoint should be when it's just barely a light pink like this. If you've gotten to a dark pink, that means that you have too much of your base in the solution. An equivalence point occurs when the moles of H plus equal or are equivalent to the moles of OH minus ions in the solution. The equivalence point is where you know you have an equal amount of each substance. An endpoint is going to occur when a tiny bit of OH minus ions are in excess, and those are able to tint the color to be just slightly light pink. That would be an endpoint when we're using a titration with phenolphthalein. All right, so this is an example of the apparatus we use for titration. We have our aqueous sample at the bottom. We're going to add a little bit using this little stopcock here. If you turn the lever to the side, it'll turn it off. If you turn it so that the lever is with the solution will go out. If you are very, very careful, you can turn it so that one drop at a time will be added. You want to swirl as you go, and when the amount of the titrant, or NaOH, is added, and if it exactly equals the amount of H pluses here, we will reach our endpoint. When you do a titration with a strong acid and a strong base, they are both fully dissociated in the water. And so when you reach your equivalence point, that means you have an equal amount of acid and base, and it will be at a pH of 7. Now, if you have a weak acid with a strong base, what happens if you have a weak acid and a strong base is that weak acid is kind of buffered, and so it will not reach equivalence point until you're at a higher pH because the base is strong. So if you have a weak acid with a strong base, you're going to get a equivalence point that is higher than 7. Here you can see the graph of a weak base with a strong acid. And so the weak base starts not at 14, but it kind of slowly makes its way through the pH scale, and so you end up with a lower pH equivalence point because you started with a chemical that did not have as strong of a basicity. We want to choose an indicator that will change in the pH range where the equivalency point would be. So if I was titrating, like we saw in the last one, a weak base with a strong acid, we saw that the pH changed around 4. So maybe we'd want to use bromophenol blue, okay, or bromescal green. If we were titrating HCl and NH3, that's what we'd be looking for, because as we saw back here, NH3 and HCl have a 5.27 equivalence point. So let's see what changes around 5.2. Well, maybe methyl red would be a good choice of indicator. Oh, we got it right. So there's a few steps to completing a titration calculation. So here's a problem. 35.62 milliliters of NaOH is neutralized with 25.2 milliliters of 0.0998 molar HCl by a titration to an equivalence point. What is the concentration of the NaOH? All right, so write down the 4 steps that it takes in order to do this problem. All right, so now I'm going to walk you step by step through this titration calculation that you have in your notes. So the notes say that we have 35.62 milliliters of NaOH. And so the first thing that we want to do is label what we know. So we know that we have 35.62 milliliters of NaOH. We also know that we have 25.2 milliliters of 0.0998 molar HCl. So now we want to find the concentration of the NaOH. All right, so now that we have everything labeled, what we have to do is we have to be able to take our concentration and our volume. We want to change it to moles. Use the mole ratio to change it into moles of NaOH, and then we can convert it back and find our molarity. Now, if you remember from solution stoichiometry, the relationship that molarity equals moles per liter, we can actually use this calculation in order to find the moles because we have molarity and we can change this to liters. So let's change that to liters. That's going to be pretty easy here. 0.0252 liters. Now, if we wanted to solve this for moles, all we have to do is cross multiply. So molarity times liters equals moles. So here we can just multiply our molarity times our liters, and that's going to equal our moles. So let's see, 0.0998 molar times 0.0252 liters equals, all right, 0.0998 times 0.0252 equals 0.00251 0.00251 moles of HCl. So we can put that right here, 0.00251 moles of HCl. Okay, I'm going to erase my work so that I can keep working with you in this small space that we have. Now, in order to get from moles of one chemical to moles of the other, we have to use our coefficients. Now, this equation is really nice. It's balanced already. So we know that we have 1 mole, 1 mole, 1 mole, 1 mole. So our mole ratio is going to be just 1 over 1. So let's take our 0.00251 moles of HCl, multiply by 1 HCl, and our unknown NaOH is on the top, equals 0.00251 moles of NaOH. All right, so now we know stuff about our NaOH. We can fill that in over here. 0.00251 moles of NaOH. But that's not our final answer. We want to figure out how much concentration, or what is the concentration of that NaOH. So, hopefully you got this work. You can pause it if you haven't. I'm going to erase it. And now I'm going to work out how to find this. So, we have our milliliters, we have our molarity, and we don't have our molarity, and we have our moles. So, we can use that concentration calculation that we had earlier. Molarity equals moles per liter, and now we can plug everything directly in because molarity is our unknown. So moles, we have 0.00251 moles over 35.62. Oh, where did I go astray there? That's right, I need to put it in liters. So 0.03562 liters equals. All right, so we know our molarity is 0.0706 molar. Let's put that in a fun color since we got the answer. Yay! And of course we want to put our units and our chemical. And that's it. That's how you calculate your solution stoichiometry using titration. All right, I'm going to walk you through the second titration calculation that is in your notes on titrations. And so let's go ahead and start once again by labeling what we know. So we know that we have 17.0 milliliters of 0.25 molar NaOH. So we're going to go ahead and put that in. NaOH. And now on the other side, we have 25.0 milliliters of H2SO4. 25.0 milliliters of H2SO4. Now, what we learned with our last problem is that we're definitely going to need all of these things to be in liters. So let's go ahead and change that to liters right away. So this is going to be 0.017 liters, and this is going to be 0.025 liters. So to find our final answer, we know we're going to need to go down into moles and convert using our mole ratio. Since here we have molarity and liters, two pieces of information, we know we're going to start with this side, change it into moles of NaOH. Then we can use our mole ratio to change it into moles of H2SO4. And then finally, we can use our moles of H2SO4 along with the liters that are given to find our final answer. So let's go ahead and start our calculations. So if you remember, we know that molarity equals moles over liters, and so to get moles alone, which is what we're solving for, we do have molarity and we do have liters, so we need to cross multiply, and we find that M times L equals moles. So let's take our molarity, 0.25 molar, times our liters, 0.017 liters, equals 0.25 times 0.017 equals 0.00425. All right, so that was here, so that must be moles of NaOH, 0.00425. What we're going to need to do next is look at the relationship between NaOH and H2SO4 by looking at their coefficients. Now, this is not balanced yet, so we need to balance our reaction. H2SO4 looks the most complicated, so let's give that a 1. If I have one H2SO4, that means that I'm going to have one Na2SO4 because the sulfates are the same. If I have one Na2SO4, that means I must have two NaOHs going in. And if I have two NaOHs, I'm going to have two waters coming out. So now I know I have my balanced reaction. In order to move from moles of NaOH, I need to multiply by my mole ratio in order to get moles of H2SO4. So if I have my 0.00425 moles of NaOH times, I'm going to use my mole ratio. I want to get rid of NaOHs. 2 NaOH goes on the bottom, 1 H2SO4 goes on the top, and so I just divide by 2, and I get 0.00225. And that is in moles of H2SO4 because my NaOH canceled. So we're going to plug that in here. 0.002125 moles of H2SO4. Okay, finally, we are looking for our molarity, and molarity equals moles per liter. I'm going to erase my step here. So since molarity equals moles per liter, I have 0.002125 moles over 0.025 liters. I'm going to divide those. And I get 0.085. 0.085. And all the way through I had 3 sig figs, so I can put a 0 at the end of that. And that is molar H2SO4 for my final answer. All right, I think you can do it too.